Hey guys, so today we're going to do the non-credit test 3 review video. It's kind of long, so hopefully we get it done quickly. Remember, test number 3 has the following checkpoints. The random variables checkpoint 3, both sampling distributions checkpoints, estimating a population proportion, the distribution of sample means, and estimating a population mean. So let's get into it. Color blindness is any abnormality of the color vision system. Gender based, roughly 8% of white males have some form of color blindness, while the incidence among white females is only 1%. A random sample of 20 white males and 40 white females was chosen. Let X be the number of males who are colorblind, Y be the number of females who are colorblind, and Z the total number of colorblind individuals. So which of the following is true about the random variables X and Y? So in order for both X and Y to be approximated by a normal distribution, two things have to be calculated. In each sample, we need to have that the sample size times the probability and the sample size times 1 minus the probability. We need both of these to be at least 10 in both groups. So we can just calculate that out. So for males, our sample size is 20, and our probability is 0.08. 1.6. And then we would do the same thing, 20 times 1 minus 0.08, and we should get 18.4. So because both of the males in the male group, both numbers are at least 10, X cannot be approximated by a normal random variable. And we're going to do the same thing for the females. We're going to do, we have 40 females times the success probability is 0.01. And you'll see that's 0.04. That's also not at least 10. So because both of these are not met, neither X nor Y can be approximated by normal. Suppose the scores on an exam are normally distributed with mean 75 and standard deviation 8. The instructor wants to pass anyone who scores above a 69. So what proportion of exams will pass passing score? So we're just looking to see what is the probability that X is greater than 69, where X is the grade on the exam. So we're going to do, note though that because this is a greater than probability statement, Excel won't be able to do this calculation immediately. We need to rewrite this using the complement rule and say this is 1 minus the probability that X is less than 69. And when we write it in this way, we actually can use the normal distribution function in Excel. But don't forget, when you type it in, you got to do 1 minus norm dist. Our X value is 69, our mean is 75, our standard deviation is 8, and the cumulative is always 1. And when you do that, you get 0.7734. And remember, you can always round in Excel by just adjusting them using these buttons. Suppose the scores in an exam are normally distributed with mean 75 and standard deviation 8. What is the exam score for an exam whose z-score is 1.25? So there actually is no Excel function for this. You just need to know that to calculate a z-score, we take the X value, we subtract the mean of the distribution, and we divide by the standard deviation. And knowing this identity, knowing this formula, we can actually work backwards. We can solve for X. So solving for X is just a little bit of algebraic manipulation, but we get that X is equal to Z times the standard deviation plus the mean. So from there, we know then, all right, I know the Z-score is 1.25. I know the standard deviation is 8, and I know the mean is 75. So just plugging all those in, we get that that score had to have been 85. Suppose the time to complete a 200-meter backstroke swim for female competitive swimmers is normally distributed with a mean of 141 and a standard deviation of 7. Suppose the fastest 6% of female swimmers in the nation are offered college scholarships. In order to be given a scholarship, they must complete the backstroke in no more than how many seconds? Well, we want then, if we're swimming really, really fast, the fastest 6%, that means that we're swimming significantly faster than the mean. So we're looking at who swims in the lowest 6% of the distribution. So we really are not asked to calculate any probability, but we're just trying to figure out at what value is 6% of the data below that. The fastest 6%. So in those situations, we use norm inverse. We work backwards. We know that the probability is going to be 0.06. The mean of the distribution is 141, and the standard deviation is 7. Just plugging those in right away, we get 130.1166. But it wants for the nearest whole number. So if you can't see this 130, just show fewer decimal places until there is no decimal, 130. The following histogram below displays the distribution in battery life for a certain battery model. Suppose that battery life is a normal random variable with mu8 and sigma 1.2. Using the standard deviation rule, what is the probability that a randomly chosen battery will last between 6.8 and 9.2 hours? So this is just saying, all right, how many standard deviations away from 8 are 6.8 and 9.2? 8's our mean, so that's our center. So if we just look at, say, 8 plus 1.2, oh, there's 9.2. And let's do 8 minus 1.2, 8 minus 1 standard deviation, and we get 6.8. So those are the values that we're looking at. So we've gone 1 standard deviation away from the mean in this situation, which, according to the standard deviation rule, tells us that's where 68% of our data lies. The number of days after mail out it takes a utility company to receive payment for a customer's bill is a normal random variable with a mean of 31 and a standard deviation of 6. There is a probability of 0.50 that a bill will be received later than how many days? Well, there's a really easy way of doing this, but I think 50 is just a random value in this particular question. So I'll show you how to do it with any type of probability, but in this case, it's going to be 31. Because it's the mean of the distribution, so 50% of the data is above it. But if we wanted to know another way of doing it, we would just say, we're given the probability. So it's the same situation, but we need to work backwards. So we do norm inverse again, but Excel only calculates this value if the area is to the left of a value. And when we say that 50% of a bill received later than, that means that we're looking at the greater than probability. So we need to convert this by saying 1 minus 0.50, find the left probability. Then we just do the mean and then the standard deviation. And then you'll get 31. According to the Bureau of Labor Statistics, in May 2014, the mean hourly wage of a social worker was 28.08 with a standard deviation of 1.97. Jeronica is a social worker with an hourly wage of 31.6. So what is her z-score? All right, so z-scores, we could do that formula, z equals x minus the mean divided by the standard deviation. Or Excel does have a function to calculate a z-score. It's standardized. And so we know then we can just use this function to find the z-score. So Jeronica works 31.6, so that's our x value. The mean is 28.08, and the standard deviation is 1.97. Now immediately note that Jeronica makes more than the mean hourly wage. So her value is greater than the mean. So this tells us the z-score is going to be positive. So whatever you get as your answer should be positive. Oh, there we go. So that's going to be 1.79. The lifetime in miles for a certain brand of tire is normally distributed with a mean of 22,000 miles and a standard deviation of 3,100 miles. The tire manufacturer wants to offer a money-back guarantee so that no more than 3% of tires will qualify for a refund. What is the minimum number of miles that they should guarantee the tires will last? So, no more than 3% means less than or equal to 3%. So, that's already perfect. That probability is less than or equal to something. So, 0.03 is our probability. We want the mean to be 22,000. And the standard deviation to be 3,100. So they should guarantee that their tires will last at least 16,170 miles. The distribution of the diameters of a particular variety of orange is approximately normal with a standard deviation of 0.3 inches. How does the diameter of an orange at the 67th percentile compare with the mean diameter? This one's a little tricky, I'm not going to lie. All we're looking for, it doesn't tell us anything about what the mean value is, and we actually can't figure that out. And we don't know anything about the values of x, but we do know that if I calculate a z-score, I know that z equals x minus the mean divided by the standard deviation. And if you look at this question, it's actually only asking you to find this value. What is x minus the mean? Because that quantity tells you how the two are related to each other. How do they compare? So we can figure this out by just saying then that, oh, x minus the mean is equal to the standard deviation times z. So all we have to do now is figure out, well, what's a z-score for this value? Well, that's why they give you that additional information about the 67th percentile. The definition of the 67th percentile is it's the value of x where 67% of the data falls below it. So we can actually use our norm inverse function, actually norm S inverse, to figure that out. Now we're doing norm S inverse here because we're looking for the z-score, and the probability is just 0.67. So to get the z-score is 0.4399. So we can calculate that the difference between the x value and the mean is the z-score times the standard deviation, 0.03. And we get that the difference between the x value and the mean is 0.132. Now because this is positive, that means the x value is larger. So it is 0.132 inches above the mean. The heights of students at a college are normally distributed with a mean of 175 and a standard deviation of 6. One might expect in a sample of 1,000 students that the number of students with heights less than 163 is what? So, first thing we need to do is figure out, well, what's the probability that a randomly selected student is less than 163 centimeters tall? So we use, once again, norm dist. Norm dist is used whenever our inequality is less than. So our x value is 163, the mean is 175, the standard deviation is 6, and the cumulative is always 1. So this tells us in this particular college, there's about a 2.3% chance that we'll get somebody whose height is less than 163, given that the mean is 175. Now, that's not the question. It says, in a sample of 1,000, how many would we expect? Well, we just take the value of 1,000 and multiply it by the probability. And so we get 1,000 times this probability is 22.75, which we round up to say, all right, I would expect about 23 people. The weights of cockroaches living in a typical college dorm are approximately normally distributed, that's what it should say, I will add that word later, with a mean of 80 and a standard deviation of 4. So we're looking for the percentage of cockroaches weighing between 77 grams and 83 grams. So if we write this out in probability notation, we're looking for the probability that x is between 77 and 83, if x is the weight of a randomly selected cockroach. So with problems like this, when we have a compound inequality, we need to calculate two norm dist functions and take their difference. So we do norm dist of the larger value, 83, comma the mean, comma the standard deviation, and then comma 1 always. Minus, we're going to do it again, norm dist, but now the next x value that we use is the 77, the smaller one. The mean is 80, the standard deviation is 4, and our cumulative is 1. And this will tell us immediately what the probability is, like 0.54, yeah. But it wants it rounded to the nearest whole number, and if you look at the problem, it wants the percent. So what we need to do first is convert this number to a percent by multiplying by 100, and then rounding this to the nearest whole number of 55. All right. The following displays two normal distributions. Which of the following are true? So the mean of A is less than the mean of B. Well, the mean of the normal distribution is just where it's centered at, where the highest peak is. So the mean of A looks to be, I don't know, 1, 2, 3, like it looks to be about 4. It's right where it's clustered at. And then B is significantly farther. So this is true. 1 is true. The mean is less. The standard deviation of A is less than the standard deviation of B. Well, standard deviation just refers to the spread of the distribution. Which distribution is more spread out, A or B? And if you look at it, A is not as spread out as B. B is really spread out, which tells us that the standard deviation of B is larger than the standard deviation of A, or the standard deviation of A is less than B. So 1 and 2 are now correct. And then the last one, the area under the curve of A is less than B. That's not true because both of these are specified to be normal distributions, so we know the area under both of them are 1, regardless of their variability. So that tells us that statements 1 and 2 are the only ones that are correct because both distributions have the same area. All right. The run times of a marathon runner are approximately normally distributed. The z-score for his run this week is -2. So which of the following statements is a correct interpretation of a z-score? So a z-score by definition is just the number of standard deviations away from the mean a particular value is. And that's really all we're going to say. Now, if the z-score is negative, it means the value is lower than the mean. If the z-score is positive, it means it's higher than the mean. So this week, his time was 2 standard deviations less than his average time. We are 2 standard deviations below the mean. The distribution of scores in a recent test closely followed a normal distribution with a mean of 22 points and a standard deviation of 2. For this question, do not apply the standard deviation rule. What proportion of students scored at least a 26 on the test? So we're looking for the probability that X is greater than 26, if X is the score on the exam. Now once again though, Excel can't calculate greater than probability without a little manipulation. So we're going to do 1 minus norm dist and do 26 as our X. Our mean is 22, our standard deviation is now 2, and the cumulative is always 1. So just be careful. When we do greater than probability distribution calculations, we need to do 1 minus. And so our probability to 5 decimal places, it's given to us already, 0.02275. And now with this question, the 85th percentile. So the 85th percentile refers to what is the value of X, where 85% of the data is below that value. So we can just go ahead and use norm inverse. Below the value means you can just type in 0.85. The mean is 22, and the standard deviation is 2. Enter. So the value of X is, rounded to how many? 3. 24.073. Question 15. The EPA requires that the exhaust of each model of a motor vehicle be tested for the level of several pollutants. So in one truck, it's been found to vary normally with a mean of 1.45 and a standard deviation of 0.40. So what is the 10th percentile? So we're going to do norm inverse again. The probability is our percentile value, 0.10. The mean is 1.45, and the standard deviation is 0.40. So we get that the 10th percentile rounded to 4 decimal places is 0.9374. Find the IQR. All right, well, think back to the very first chapter that we did, the EDA examining distributions. Interquartile range, or the IQR, is the difference between the first quartile and the third quartile, which means we need to find those 2 values. Now, the first quartile is also known as the 25th percentile. Think of it like first quarter, 25th percentile. So the area, that means that 25% of our data is below the first quartile. So to find it, we can just do norm inverse. The probability is 0.25. Think of first quartile as like 1/4, 25%. And then our mean is 1.45, and our standard deviation is 0.40. 0.25, 1.45, 0.6. Oh. Then the third quartile. Well, the third quartile is known as the 75th percentile. It is the value that separates the lower 75% of our data from the upper 25. The key here is lower 75%. Think 3/4. The mean is 1.45, and the standard deviation is 0.40. So those are the 2 quartiles that we need, but to get the IQR, we just take the difference, Q3 minus Q1. And notice that in Excel, I always just click the values in their representative cells. I don't ever just say, 1.719 minus 1.180. I always click the value because it keeps everything as exact as possible. So round it to 4 decimal places, and you can use Excel if you want to, 0.5396. I'm going to move these over. All right, so question 16. A study was made of seatbelt use among children who were involved in car crashes that caused them to be hospitalized. It was found that children not wearing any restraints had hospital stays at the mean of 7.37 days and a standard deviation of 0.75 days. So what is the probability that their stay is from 5 to 6 days? So the probability that 5 is less than x is less than 6. I don't need to have that percentage. There we go. So we just need, because we're looking at this compound inequality, we need to do two norm diffs. So norm diff, the larger value of x, the mean is 7.37, the standard deviation is 0.75, and the cumulative is always 1. And then we're going to do it one more time. Norm diff minus norm diff, now we're going to do 5, 7.37, the standard deviation is 0.75, and the cumulative is 1. So, enter. And we get rounded to 5 decimal places, the probability that a child will be there between 5 and 6 days. 1, 2, 3, 4, 5. Is 0.03309. Find the probability that their hospital stay is greater than 6 days. So, once again, we're looking at a greater than probability calculation. So we're going to do 1 minus norm dist, 6, 7.37, 0.75, comma 1. And we get that the probability is 0.96613. It's sad. All right, question 17. We've moved on to sampling distributions checkpoint 1 material. So in June 2017, a survey was conducted. In 1973, the Roe v. Wade decision established a women's constitutional right to an abortion, at least in the first 3 months. So the results of their survey, their random sample, were below. Of the sample, 29% said yes, 66% said no, and 5% said they were unsure. So which of the following is true? Well, the values that we get from a sample are always known as statistics. And we use statistics to make claims and inferences about the unknown population parameter. Parameters describe the values of a population. We want to estimate them because we do not know them. So anything you calculate from any sample, any experiment, is known as a statistic. So same thing with number 18. We did a survey and said, do you exercise at least 30 minutes? And the people responded in that way. Because they responded from a sample, they're statistics. So with sampling distributions, either proportions or means, the larger the sample size, the smaller the variability, which means the smaller the standard deviation. That's why you want a large sample size. So the variability changes based on the sample sizes, but regardless of the sample size, the sampling distribution will always be at the population value, regardless of the sample size. So in this plan, in number 19, we're looking to either sample 400 voters or sample 1,600 voters. But the sample proportion, let's see. So let's read it. The sample proportion of is likely to be close to true. B is true. And while they're centered at the same value, because the variability of the sampling distribution with 1,600 is smaller, it means more values are clustered at that mean. So in this case, we want to have a larger sample size because we're more likely to be closer to the true population proportion. That's the exact same question, so I'm going to say the answer is A. We want to sample 900. It's closer to the true population proportion. However, 21 is a little bit different, but we're either going to sample 100 people or 900 people. So this question is testing you on whether or not you know where the distributions are centered. So different sample proportions would result each time, but for either sample size, they will have their centers at the true value. That is true. Their variability is different, but they are both centered at the mean, at the true population value. And this is the exact same question, but now we're doing 400 and 1,600. So different sample proportions will result each time, but for either sample, they will have their centers at the true population value. 23. A political polling agency wants to take a random sample of registered voters and ask whether or not they will vote for a certain candidate. One plan is to select 400 voters, and the other is to select 1,600. So the first idea with this question is to know that the variability in the sampling distribution with 1,600 voters is going to be smaller than that of 400. So if you look at all these answer choices, they're all in terms of the sample size 400. So that means we're looking for the standard deviation is larger because a smaller sample size gives you a larger standard deviation. So that's going to be answer choice B or D. So now we just need to think about, well, which number is it? How many times larger? Well, if I'm going to go from 400 voters to 1,600 voters, that means I'm quadrupling the sample size. I'm multiplying the original sample size by 4. Now, if you know, though, the formula for the standard deviation of a sampling distribution for a sample proportion, we know that it's the square root of p times 1 minus p divided by the root n. Now, there's an algebraic proof for this, but I'm just going to say the idea comes from the square root function here. So if I'm quadrupling by multiplying by 4, I have to take the square root of that multiplier, which is then going to be 2. The square root of 4 is 2, so it's going to be 2 times larger. All right, I'm going to move to a different page. All right, juries should have the same racial distribution of the surrounding communities. According to the U.S. Census Bureau, 18% of residents in Minneapolis are African American. That is a parameter. It describes, it's going to be the mean of our sampling distribution. 18% is our parameter for the percentage of residents who are African American. So then we're going to sample 100 people to see if juries, let's see, a local court will randomly sample 100 state residents and will then observe the proportion of the sample who are African American. How likely is the resulting sample proportion to be between 0.066 and 0.294? Well, what we need to calculate first is, now that we're dealing with a sample proportion, we need to find the standard deviation of its sampling distribution, or the standard error. So the standard deviation is going to be the square root of p times 1 minus p divided by n. And I just click the values, and that's why I put them in first. But a square root of p times 1 minus p over n. Be careful with parentheses. So the standard deviation here is 0.038. Now, there are two ways to really do this question at this point. I prefer to do it the way I'm going to do it in this video because the kids like it easier. It's easier for them to do, so I'm going to do it that way. So we're going to do the probability that our sample proportion is between 0.66 and 0.294. We're going to look at this probability. And if you look at it, though, it behaves the same. I'll just go ahead and tell you that we can model this with a normal distribution because n times p is 18, and n times 1 minus p is 82. And you can calculate that by doing 100 times 0.18, 100 times 0.82. And because we can model it with a normal distribution, we're going to use norm dist. So we're going to do norm dist, but it behaves the same way, even though we're dealing with proportions. Our first value is the larger of the two, 0.294. Our mean is 0.18. Now our standard deviation is the one that we calculated a little bit ago. And then our cumulative is 1. And now we're going to do minus, do it again, norm dist, minus norm dist, now do the smaller value, 0.066, 0.18. Click the standard deviation so it doesn't round it, comma 1. And what we're going to get is something like 0.9969. So if we convert this to a percentage, you'll see that we're about 99.7%. So the other way that you could have done this question is to do the standard deviation rule. Take your mean, subtract 3 standard deviations to the left, and you'll get 0.066. Take your mean, add 3 standard deviations, you'll get 0.294. So the standard deviation rule tells you that, approximately 99% of the data is within 3 standard deviations. 25. A distribution of a single statistic when repeated random samples of the same size from the same population refers to which of the following. That's definition of the sampling distribution. Suppose that 20% of the residents in a certain state support an increase in the property tax. An opinion poll will randomly sample 400 state residents and will then compute the proportion of the sample that support a property tax increase. How likely is the resulting sample proportion to be within 0.04 of the true proportion? So, we just need to see how many standard deviations away from the mean is 0.04. Well, let's calculate the standard deviation. It's the square root of p times 1 minus p over n. So the square root, our p is 0.20 times 1 minus 0.20 divided by our sample size of 400. And we get the standard deviation is 0.02. Now, we're looking to see how likely is it to be within 0.04. So our standard deviation is 0.02. So if I do 2 times 0.02, that's 0.04. Therefore, it's just asking us what percentage of our data is 2 standard deviations away from the mean. 2 because 0.04 is 2 times 0.02. So the standard deviation rule tells you that's about a 95% chance. Which of the following best describes the sampling distribution of a statistic? Well, it is the distribution of a single statistic from repeated random samples of the same size from the same population. A social scientist wishes to conduct a survey. She plans to ask a yes-no question. Which of the following, one is to sample 100 people and the other one is 900. Same thing as before. The sample of 100 people is going to be large, or the standard deviation of the sampling distribution of 100 people is going to be larger than the sample with 900 people. So, how many times larger? Well, to get from a sample size of 100 to 900, we multiply by 9. Now, because our standard deviation formula has a square root, we take the square root of that multiplier. So the square root of 9 is 3. Therefore, it's 3 times larger with a sample size of 100. In a study of the effects of acid rain, a random sample of 100 trees from a particular forest is examined. 40% of these show some signs of damage. So which of the following is correct? Now, from the sample, 40% are examined. So 40 is a statistic. In a study of the effects of acid rain, a random sample of 100 trees from a particular forest are examined. 40% of these show some signs of damage. The sampling distribution of the proportion of damaged trees is approximately normal. That's actually true. N times p hat. If the sample of 1,000 trees was examined, the variability would be larger. Well, no, that can't be it because 1,000 is a larger value than 100, so the sample size is larger, which means the variability is smaller. None of the above. All right. If we took another random sample of trees, we find that 40% of these would show some signs of damage. Well, that's not true. There's something called sampling variability, which means that from sample to sample, the results and statistics that you calculate are going to differ in each sample. So the answer is A. All right, a survey asked a random sample of 1,500 adults in Ohio, so that's our sample sizes. N is 1,500. Let p hat denote the proportion in the sample who say they support the increase, but we also know that the population parameter is 0.30, so we're going to call that the mean. And we just want to know what's the standard deviation. Well, the standard deviation is the square root of p times 1 minus p divided by n. Round to 4 decimal places, 0.0118. All right. Suppose that 88% of all dialysis patients will survive for at least 5 years. So that's our mean, 0.88. Actually, that's I'll just call it p. It's 0.88. Now we're going to do a sample of 100 people. And we want to know what's the probability that those surviving after 5 years is greater than 80%. Actually, I should really say probably that p hat is greater than 0.80. So we can use a normal distribution to do this, because if we did 100 times 0.88, we get 88. That's greater than 10. And if we did 100 times 1 minus 0.88, we get 12. So because both of those numbers are at least 10, we can use the normal distribution to solve this. But look at our probability statement. We're looking for greater than 0.8. We can't do that in Excel right now. We have to change it a little bit. So 1 minus norm dist Actually, I'm going to calculate something first. I need to calculate standard deviation. So the standard deviation first is square root of p times 1 minus p all over n. I'll click that, but then change it to 100. There we go. So now we want to know what's the probability that p hat is greater than 0.8. So like I was saying, we can't do it right now in this way. We have to do 1 minus norm disk. And we're looking for greater than 80, so we're going to do 0.80. The mean is 0.88. The standard deviation is that 0.032 value, and then the cumulative is always 1. So the probability is 0.99309. That's good. Which of the following statements about the sampling distribution of the sample mean x bar is true? Well, there are two things we need to know of. The sampling distribution of a mean of x bar is normal if the population is normal. That's the first thing. So, that's B. And also, if the population is not normal, then what we need is that the sample size is large enough. So if the population is not normal, as long as the sample size is at least 30, the sampling distribution will be approximately normal. That's called the central limit theorem. So that is what A says. The distribution is normal regardless of the shape of the population as long as the sample size is large enough. Well, what is considered large enough? At least 30. C. The distribution's mean is the same as the population. That is true. Sampling distributions have the same mean as the population, and the distribution standard deviation is smaller. That's true. The standard deviation of the sampling distribution is always smaller than that of the population. So if you take repeated random samples of size 20 from a population with a mean of 60 and a standard deviation of 8. So which of the following statements is true about the sampling distribution? Well, the distribution is normal regardless of the shape of the population because the sample size is large enough. That's not true in this situation because the sample size is only 20 and we need it to be 30. The distribution will be normal as long as the population is normal. That's true. And the distribution's mean is the same as the population mean. That is also very true. And the sampling distribution standard deviation is larger than the population. That's not true. Sampling distributions always have a smaller standard deviation. So we have three distributions here. One is the population, and the other two are standard deviation or are sampling distributions for size 5 and size 30. And I think what it wants us to do is estimate the population mean. Well, all three distributions are all going to have the same mean. So it really is just my piece of advice is knowing that they're sampling distributions, they have the same mean as the population. So regardless, they're all going to be centered at the same thing. So look at the one that's most normal. It's centered at 3. All of them are going to be centered at 3. Same as this one. We have three distributions. One's a sampling distribution of size 40. That's going to be the most normal one. One's going to be of size 5, and there's a population. So let's just use the most normal one. We know that there's sampling distributions of the same from the same population of different sample sizes. Well, this normal one is centered at 8, so that's the most likely value for the population mean. All right. Suppose that a candy company makes a candy bar whose weight is supposed to be 50 grams. So the mean is 50 and standard deviation is 2. If the company sells them in packs of 4, what can we say about the likelihood that the average weight of candy bars is 4 or more grams lighter? So the mean is 50. Our population standard deviation, sigma, is 2. And our sample size is 4. So let's just first calculate the standard deviation of the sampling distribution. Well, for means, that formula is a little different. With proportions, it's the square root of p times 1 minus p over n. For means, it's sigma divided by the square root of n. Population standard deviation divided by the square root of the sample size. So the standard deviation is 1. So we want to know, what's the probability that a randomly selected, that the average weight of the bars in a sample of 4 is 4 or more grams lighter? Well, if they're advertised at being 50, that means we're looking at 4 grams lighter is 46, but we're saying more than 4 grams lighter, so 46 or less. So because the population is normal in this case, the sampling distribution is normal, even though the sample size is small. So norm dist, 46, the mean is 50, the standard deviation is the one we calculated, not the population standard deviation, but the sampling distribution standard deviation, comma 1. And you're going to get something, I think, really, really small. Yes. So 3.167E05, that is scientific notation. It means move the decimal to the left 5 times. If you don't like scientific notation, just click the cell, go up to number, and change it from general to number. And right now it's giving us too few decimal places, so just keep extending it, and there we go, 0.00003. So what this tells you is that it is extremely unlikely for this to occur, as the probability is very close to 0. Oops. Well, that's not the answer choice I wanted. All right, exact same question, but now everything's a little different. So we're specifying the mean of the bags is 30, the population standard deviation is 3, and in this case is 9. And so once again, we're looking for, let's just calculate the standard deviation. Well, it's just going to be sigma divided by the square root of n, 3 divided by the square root of 9, which is once again 1. But this question is a little different. It wants the probability that the average weight of the bags in a pack of 9 is 2 or more grams lighter than advertised. So 2 grams lighter is going to be 28 grams. So 2 or more means we're looking at the less than 28. But now it's the same as before. Norm dist, the value of x is 28, the mean is 30, the standard deviation is the new standard deviation we calculated, comma 1. So 0.2275. So if we convert this to a percentage, because all these answer choices are in terms of percents, we'll get 2.275, about 2.3% chance, which is about 2.5%. You could easily solve this one using the standard deviation rule as well, but it's just easier this way. When the population is not normally distributed, the sampling distribution of the mean approximates which of the following? It's normal then only if the sample size is large enough. That's the central limit theorem. Question 40. In which of the following scenarios would the distribution of the sample mean be normally distributed? Well, we take random samples of size 10 from a population of unknown shape. Nope. We take repeated random samples of size 15 from a population that's normally distributed. Yes, as long as the population is normally distributed, the sample size that we do does not matter. We take repeated random samples of size 50 from a population of unknown shape. That's also true, because if the population shape is unknown, as long as we sample more than 30, it's fine, which means D is wrong because we're only sampling 25. All right, question 41. A factory produces plate glass with a mean thickness of 4, so the mean is 4, and a standard deviation, sigma, of 1.1. A sample of 100 sheets is going to be selected. What is the probability that the average of the 100 sheets is less than 3.74? So in order to do this, though, we need to find the standard deviation of the sampling distribution, which we know is going to be sigma divided by the square root of n, 0.11. So now we can use the normal distribution function in Excel to find this probability. And the reason why is we don't know anything about the population shape, but our sample size is 100. It's more than 30, so we can assume that it's approximately normal. So do norm dist, 3.74, our mean is 4, our standard deviation is the 0.11, comma 1. And round it to 5 decimal places, 0.00905. All right. Sorry, hold on. My dog. The number of hours a light bulb burns. before failing varies from bulb to bulb. The distribution of burnout times is strongly skewed to the right. The central limit theorem says that, well, the central limit theorem, if you remember, just says that as the sample size increases, at least 30, the distribution is going to be approximately normal. It doesn't say anything else about the average or whatnot. So you're just looking to see the average burnout time of a large number of bulbs has a distribution that is close to normal. Remember, a lot of students get D and E confused. E says the average burnout time of any number of bulbs. So that's almost the same, but any number of bulbs kind of implies that it could be a small sample size. So we don't say that. The average burnout time of a large number of bulbs has a distribution that is close to normal. 43. A machine is designed to fill 16-ounce bottles of shampoo. When the machine is working, it dispenses 16.05 ounces with a standard deviation sigma of 0.1005. If 4 bottles are randomly selected, then 95% of the means calculated should occur in what interval? So there's a hint for this question. It says the standard deviation rule says that 95% of the observations are within how many standard deviations away from the mean. So we actually need to first calculate the standard deviation of the sampling distribution. The standard deviation. So we need to do sigma divided by the square root of n. And then what the standard deviation rule tells us is that 95% of our observations are within 2 standard deviations from the mean. So we're going to calculate a lower and an upper bound with this. So we're going to do the mean minus 2 standard deviations. So just notice how I'm doing the mean minus 2 times the standard deviation, and we get 15.9495. And we're going to do the same thing. We're going to do the mean plus 2 times the standard deviation that we calculated, 16.1505. So 15.9495 to 16.1505. Let me make sure I typed that in right. 15.9495. Okay. Suppose that the distribution for total amount spent by students vacationing for a week in Florida is normally distributed with a mean of 650 and a standard deviation of 120. So the mean is 650. Sigma, the population deviation, is 120. We're going to sample 5 students. All right. So what is the probability that a simple random sample of 5 will result in a average spending between 600 and 700? So in order to do this, though, we have to once again calculate the standard deviation of the sampling distribution of x bar. So we just take equals sigma divided by the square root of n. 120 divided by the square root of 5. And once we have that, we can just calculate our probability statement. Notice that we're doing a compound inequality once again, so we have 2 norm dist functions to calculate. Norm dist, our upper is 700, comma the mean, comma the standard deviation, not 120, but the 53.665 value, comma 1, minus norm dist 600, comma the mean, comma the standard deviation, comma 1. Once we get this, round it to 5 decimal places, 0.64851. All right. Moving on to confidence intervals. So we're done with sampling distribution, checkpoint number 2 at that point. So for a class assignment, let me move on to another page. For a class assignment, a group of statistics students set up a table near the parking lot. They asked students who passed by to complete a quick survey about whether they support the building of a multi-level parking structure that would add 425 new spaces at the college. They calculated a 95% confidence interval. To which population does this confidence interval apply to? Well, they shouldn't have calculated an interval regardless because their sampling method is a convenient sample. They just put a table down and asked random people. So Because of that, the fact that they created a confidence interval is bad. It doesn't pertain to any population. So one of the criteria of a confidence interval, or one of the assumptions that you have to make, is that the results that you get from your experiment or random sample are random. Because if it's not random, you can't really generalize it to the population as a whole. So in this case, even though they calculated the interval, it doesn't pertain to any population because their sampling method was poor. It was a convenient sample. All right, so 46. The administration at GSU wants to estimate the number of parking spaces they will need next year. They survey 80 students, 75 of which say they drive to campus. So which of the following is a reason that the admin should not calculate a confidence interval? Well, three things need to be met. Three conditions need to be met in order for a confidence interval to be constructed. The very first is that your sampling method has to be random. And so it says they survey 80 students. It doesn't say how. It doesn't specify if it's random or not. So that's the first thing that we need to be weary of. So that's the first checkpoint. The sample needs to be random, but we don't know what it is, if it is. Now the second condition is that in order to construct a confidence interval for a sample proportion, we have to have that the number of successes, the number of failures are at least 10, meaning n times p and n times 1 minus p are at least 10. So we can calculate that. So our sample size is 80. Our probability, our p-hat, is 75 out of 80. Not 57, 75 out of 80. So that number is 75. That's met. We have enough, that's at least 10. But if we calculate the other one, 80 times 1 minus 75 over 80, you're going to see that's 5. So our value of n times 1 minus p-hat is not greater than 10. Now, think about what these numbers mean in the context of the problem. N times p is 75. We had 75 students say that they drove to campus, which means we had 5 students tell us they do not drive to campus. So that's what n times 1 minus p-hat represents. It's the actual count of those who do not drive to campus, and that's 5, which needs to be 10. It's too small. So all 3 of these need to be checked. This is the exact same question, just a different scenario. So I'll let you kind of figure out why this is the way that it is. But the sample does not specify that it's random, once again. But in this one, it's a little bit different. Only 7 received the concert brochure. So if we do n times p, 100 times 7 out of 110, we'll get that n times p-hat is not greater than 10. And that number is going to be 7. And that value represents the number who received the brochure by mail, and that's not at least 10. So once again, all 3 of those need to be checked, but in this case, just pay attention to the problem. That's not the n times 1 minus p-hat, it's n times p-hat that's too small. All right, an interactive poll on the front page of CNN asked its readers if they would consider voting for Herman Cain. From the results of that survey, they calculated a confidence interval. So to what population do these conclusions apply? Well, this is just like that question a little bit ago, where we have to consider how we sampled the people to get this information. And once again, it's not a random sample. It's a voluntary response sample. People who watch CNN are the most likely people to see it, and you volunteer to respond. They asked you to call in. So because of that, it's a voluntary response sample. It's not a random sample. Therefore, they shouldn't have constructed that confidence interval. It doesn't make any sense to any population. All right, so it seems here we have a confidence interval for proportions now to do. So when I do a confidence interval for proportions, I start off by saying, what is p-hat? What is n? Based on that, what's our standard error? What's the z-score, or the critical z-value we need? What's the margin of error? And we use all that to calculate a lower and upper bound for the interval. So we just got to read the question. 1,180 people were surveyed. Overall, do you support or oppose allowing gays and lesbians to marry legally? So 1,180. Of that 1,180, only 439 said yes. So our p-hat is 439 divided by 1,180. Our standard error then is the square root of p hat times 1 minus p hat divided by n. Same formula as before, we're now using p hat instead of p. And now it looks like we want a 95% confidence interval. Now this critical z value is something that you just need to memorize. So we have a z-score for 90% confidence, a z-score for 95% confidence, and a z-score for 99% confidence. We can use the norm S inverse function to figure this out, but really just memorize them. If you do it, you'll get that the z critical value for 90% confidence is 1.645. The z for 95% is 1.96, and the z for 99% is 2.576. And you can just take those for granted. So the z-score for, in our case, 95%, we're going to put 196 here. And the last thing we need to calculate is the margin of error of this confidence interval. And the margin of error is just calculated by taking that standard error we just found, multiplying by that critical z value. So once we have all of this information, it's pretty easy to get the confidence interval. We just got to take our p hat. P hat is called the point estimate, and we subtract the margin of error. And there's our lower bound. And then we're going to take our p hat and add the margin of error. And all of our answer choices are rounded to 3 decimal places, so we're going to do the same. So what we get is that our confidence interval is 0.344 to 0.4. This tells us we are 95% confident that the true proportion of all American adults who support same-sex marriage is between 0.344 and 0.4. All right, now the nice thing is, once you have all of these things typed into Excel like this, it really is just, you can really just change the numbers and Excel will immediately recalculate confidence intervals for you. Once you, that's one of the reasons why I click on the values instead, because this is going to do the formula with whatever values in the cell that you indicated. So to do this one, I'm not really going to go through this one completely, but I'm just going to update the values that need to be updated and then just find the answer immediately. So in our new situation, we had a survey of 1,218. That's our sample size. And our p-hat in this case is 469 out of 1,218. And what you'll notice is that Excel has been updating everything immediately. It calculated the standard error, root p-hat times 1 minus p-hat over n. The critical z value we would have to update, maybe, but we're still at 95% confidence. Therefore, we don't have to change it. And so what it did is it automatically calculated our lower and upper bound based on how we calculated it in question 49. So if you want more practice with doing it, just try and repeat it the way I did it in question 49. But we know just immediately then that our interval is 0.358 to 0.412. Same thing with question 51. Our sample now is, so let's take a poll of 3,862. That's our new sample, 3,862. Now we want a 99% confidence interval, so we have to change our critical z-score to 2.576. And also, we have to change our p-hat to, in our survey, in our random survey, 3,103 out of the 3,862. And changing those, Excel automatically updates it, but if you want to see how I did that before, go back to question 49. But we see immediately our confidence interval is answer choice C. So we are 99% confident that the true proportion of GSU juniors who believe that they will immediately be employed after graduation is between 0.787 and 0.82. All right. Changing the confidence level, or making a more precise interval. So in the months leading up to an election, news organizations conduct many surveys to help predict the results. Often, news organizations will increase the sample size in the last few weeks before the election. So which of the following is the primary reason they will increase the sample size? Well, increasing the sample size, if you remember from sampling distributions, decreases the standard error. It makes our standard error smaller. Now, in terms of a confidence interval, making the standard error smaller makes the margin of error smaller, which means our interval is more narrow. It's more precise. A larger sample size is a narrower confidence interval. Question 53. We know that narrower confidence intervals give us a more precise estimate of the true population proportion. So which of the following can we do to produce higher precision? So higher precision means a narrower confidence interval. So just like the last question, one way of doing that is increasing the sample size. In addition, and this is going to sound a little counterintuitive, but look at your D-scores for the various levels of confidence that we have. For 99, it's 2.576. That means we get a wider interval with 99%. 95%, we get a slightly smaller one because our multiplier is less. And with 90%, we get even less. So we can select a lower confidence level or increase the sample size. That will give us our highest precision in terms of a confidence interval. All right. 54. We want to know if we need enough student parking spaces, so the administration conducted a survey to determine the proportion of students who ride a bike to campus. Of the 126 students surveyed, 7 ride a bike. Well, this is just like the questions we did in the very beginning. 1, we don't know if it's random. 2, the count of bike riders is still too small. It needs to be at least 10, which means that n times p hat is not greater than 10. N times p hat is 7. N times 1 minus p hat is 119. Just like before. Same question. Same thing with question 55. We don't know if it's random. The actual count of students who do not believe hookah is less harmful is too small, because 45 people think that hookah is less harmful, which means only 5 think it's not less harmful, which means n times 1 minus p hat is not greater than 10. It's actually 5. 56. In April and May of 2011, the Pew Research Center surveyed cell phone users about voice calls and text messaging. They found that 55% of those who send 51 or more text messages per day prefer to be contacted by text message rather than by voice call. Oh my gosh, that's so true. The margin of error for this sample was 5.7. So what does this tell you? So this just tells you that the population proportion is most likely to be within 5.7% of the sample proportion from a randomly selected sample. And if you look at D, it kind of makes sense, but the idea is that it says we are sure. We can't really be 100% sure, so that's important to kind of think about with these questions, making sure you pay attention to the wording of everything. All right, 57. Okay, a 95% confidence interval is 73.1% to 76.9, and we're just looking to see the use of texting. So what does interpreting a confidence interval, we just say we are a certain degree confident that the true parameter of interest is between blank and blank. So in this case, we are 95% confident that the proportion of all cell phone users who use text messaging is between 73.1 and 76.9. We don't make inferences or anything about a sample. We make inferences about the population, all cell phone users. So we can be 95% confident that the proportion of all cell phone users who use text messaging is between 73.1 and 76.9. Same thing with this one. We're looking to see the proportion of California residents who say that marijuana should be legal. So based on the results, 95% confidence interval is 0.506 to 0.554. So their interval specifies a majority say that it should be legal. So we are 95% confident that between 50.6 and 55.4% of California residents say that marijuana should be legal. And then you're done. That's your interval. And be careful with letter C. Know the intended population that you assessed. We surveyed California adult residents, not all Americans. So it's of California residents. In a Pew Research Center report from January 2015, 37% of American adults said that genetically modified foods are generally safe to eat. The margin of error is 3.1. So what does this margin of error tell you? Well, it tells you that we are 95% confident that the population proportion is within 3.1% of the sample proportion? Yes. You're 95% confident that the population proportion is within 3.1% of the sample proportion of 3.7%. A New York Times CBS poll surveyed 1,027 adults nationwide about race relations in the U.S. Of the sample, 61% responded that race relations in the country are generally bad, and they constructed a 95% confidence interval for 0.58 to 0.64, which of the following is an appropriate interpretation of the 95% confidence interval. So we are 95% confident that the proportion of all Americans who said that race relations in this country are bad is between 58 and 64. Be careful. There is a 95% probability, or we are 95% confident. We are 95% confident, not 95% probability. Be very careful about the wording. Question 61. A distribution for the weight in pounds of a population of 4-year-old boys is displayed below. And we want to know which graph best represents a distribution of sample means for 600 samples each with a sample size of 5. Well, sample size of 5 is kind of small, so our sampling distribution would not be this clustered around the mean. It's impossible. Not impossible, but it's just highly unlikely. A sample size of 5 wouldn't produce a histogram like this. It doesn't even look like the population at all. Uh-oh. That changes my answer to 60. So that leaves histogram C. It's going to be slightly more normal in the population, centered at the mean, so choice C. Same thing here. We have 3 groups, and we want to know which graph best represents a distribution of sample means for 500 samples of size 4. So the sampling distribution sample size is still small, so it's not going to be this clustered around the mean. It's also not going to be as variable as the population. A sampling distribution has a smaller variability, and it's going to be a little bit more normal too, so that means it's answer choice A. So, consider sampling heights from the population of all female college soccer players. And the female soccer players have a mean height of 69 inches and a standard deviation of 3.6. So suppose you randomly sample 95 values from this population and compute the mean. Then we repeat this several times. So which of the following is the best approximation for the mean of our 5,000 sample means? Well, this is just assessing you on, do you understand the relationship between the population mean and the mean of the sampling distribution? They are the same. So it's 69. Same exact question. Same question. 85. Which of the following is the best approximation for the mean of our 10,000 sample means? 85. It's the same as the population mean. This one's slightly different. Suppose you have a large population with mean 78 and standard deviation 7.2. We're going to sample 96 values from the population and compute the mean. Then repeat this several times. So which of the following is the best approximation for the standard deviation of our 10,000 sample means? Well, now we need to know, well, what is the standard deviation of the sampling distribution? It's the population standard deviation divided by the square root of the sample size. Note that our sample size is not 10,000. The sample size is 96. 7.2 divided by the square root of 96. 0.734, 0.73. The bottle of Maria's favorite sports drink says that it holds 20 fluid ounces, but she suspects that it's different. Maria takes a random sample of 25 bottles, so let's just write N is 25. In Maria's sample, the mean is 21, actually the population mean is 20. X bar, her sample is 21.5, and then sigma The population deviation is 2. So we want to know, finding a random sample with a mean this high in a population is unlikely. So we just want to know, what's the probability that we would get a sample mean of 21.5 or more? Let's just look at it in terms of probability. Now, in order to do this, though, we have to first calculate the standard deviation of the sampling distribution. So we calculate sigma divided by the square root of our sample size. And I'm just clicking. So we get our standard deviation is 0.4. And now we can just calculate this probability. It's approximately normally distributed because let's see, approximately. Yeah, so we're going to do equal to 1 minus norm dist, 1 minus because we're doing greater than, 21.5. The mean is 20. The standard deviation is 0.4, comma 1. And so when we hit enter, we get that that probability is very, very small. So if our probability is very, very small, that means it is very unlikely. So true. All right, same question, just different scenario. N mean x bar sigma standard deviation probability that x bar is less than 6.6. So the package of a particular brand of rubber bands is that the bands can hold a weight of 7. That's our mean. So we take a random sample of 36 of those rubber bands and say that the mean breaking weight of those rubber bands is 6.6. And we want to see, we know that the population standard deviation is 2. So we want to know, finding a random sample with a mean this low in a population of mean 7 is very unlikely. So we just want to know, what's the probability that our sample mean is less than 6.6, this low, 6.6 or lower. So in order to do that, we have to calculate the standard deviation of the sampling distribution. So sigma divided by the square root of n. And then now we just do norm dist. Norm dist because we have less than. We do our 6.6 value. Our mean is 7. Our standard deviation is the 0.333, comma 1. Now in this case, it's kind of tricky. Is a probability of 12% considered very unlikely? And the answer to that is no, it is not. If something occurs about 12% of the time, it can happen. Not very often, but it does happen. It's not very unlikely. So that's important to kind of see. Before, our probability was essentially 0, which means it's very unlikely. Okay, wording. What do you expect to have, which do you expect to have less variability? A sampling distribution with sample size n is 100, or a sampling distribution with a sample size 19? Well, all we have to know is that if our sample size is larger, it has less variability. So a sampling distribution with size n is 100. Hospital A records an average of 54 births a day. Hospital B records an average of 11. So which hospital is less likely to record an average birth weight of 3,447 grams or more? Well, that just means which distribution is less likely to have values away from the mean. Well, hospital A has more births, so its values are more likely to be closer to the population mean. So which is less likely? Hospital A, because the mean will typically be closer to 3,147. And why is that? Because it has a smaller variability. What do you expect for the variability of a sampling distribution? Well, regardless, it's always less variable than the population. 2 bottling plants package a certain type of sports drink. Suppose the mean volume, bottling plant A approximates 44,902 sports drinks per day. Bottling plant B approximates 177,926. On a particular day, which bottling plant is less likely to record a mean volume of 21 fluid ounces for that particular day? Which means Which distribution is more likely to be closer to 20? Well, definitely bottling plant B because it has a significantly larger sample size. Consider sampling heights from the population of all female college soccer players in the U.S. Assume the mean height of female college soccer players is 67 and the standard deviation is 3.6. Suppose we randomly sample 100 values and repeat it 5,000 times. Which of the following is the best approximation for the standard deviation? Well, once again, this is just saying what's the best approximation of the standard deviation of the sampling distribution, which is sigma divided by the square root of your sample size. Our sample size is 100. So 3.6 divided by the square root of 100 is 0.36. All right, so students are weighing chocolate candy for holiday baskets. The distribution for a population of weights is graphed below. Suppose that 5 students each take a sample of 4 candies and they make a dot plot of their 5 sample means in the classroom board. Which of the following dot plots is the most plausible? Well, if you look, our initial distribution, I guess, looks to be between like, I don't know, something less than 1, maybe 0.25, all the way to a little more than 5, or a little more than 4. And it's a sampling distribution. It's going to have a smaller variability. Now, because our sample size is so small, I would highly say that dot plot C is very unlikely. They're not going to be that clustered together. So what we're going to do is let's just look at the sampling distribution standard deviation. We know that the distribution of the candies is, go the other way, 0.5. And divide that by the square root of the sample size, 5. Is that 5? Oh, 4, I'm sorry. They randomly sampled 4, not 5. So our standard deviation of the sampling distribution is about 0.25. So we're just going to look which distribution or which dot plot has the standard deviation of about 0.25. Well, 1.5 is the middle here, but it goes all the way up to 2.5 and 0.5. So it looks to be about 1. But if you look at B, we're centered at like 1.5, and we're about, generally around 0.25 away from the mean. So I'm going to say that it's dot plot B. All right, same exact thing. Our sample size, though, is 10. So we have a population. This one's actually easier because our sample size is still kind of small, so we're never going to see this amount of clustering like this. This one, the range is basically the same as the population, so it's going to be slightly smaller than the population. So we're going to say go with A. All right, figure A represents the weight of a sample of 26 pebbles, each weighed to the nearest gram. Figure B represents the mean weight of a random sample of 3 pebbles with the mean weight rounded to the nearest gram. So what is the difference between the value represented by the X and A and B? Well, A represents the weights of the individual pebbles, and B represents, each X represents the mean of a random sample of 3 pebbles. So A. This is the exact same question. So we have 30 chocolate individually weighed, and in this one we have the means of 5 chocolates. So what's the difference? The X in figure A is the mean for a single chocolate, while the X in figure B represents the average weight of 5 chocolates. A doctor is measuring the average height of male students at a large college. The doctor measures the heights in inches of a sample of 40 male students from the baseball team, and he constructs this interval. Which of the following conclusions is valid? Well, none. And the reason why is he's interested in the heights of all the males at the college, but he's sampling just men from the baseball team. So, yeah, no conclusions can be drawn. A marketing student is estimating the average amount of money that students at a large university spend on sporting events. So he asked a random sample of 50 students at one of the football games, and he computes a 90% confidence interval. So which of the following is valid? Well, that is the exact same thing. We're trying to make a claim about all sporting events, So why sample one football game? Doesn't make any sense. Number 79. A statistics class is estimating the mean height of all female students at their college. So they select a sample of 36 females and measure their height. The sample mean is 65.3, and then the sample standard deviation, SX, is 5.2. So what is a 90% confidence interval for the mean height of all female students at their school? So we want a 90% confidence interval, 0.90. Now what is very important to understand is that because we're using the sample standard deviation to do this confidence interval, we can't use a z-score anymore. We have to use a t-score. And that's because we're using the sample standard deviation. So the t-score is defined or determined by what's called the degrees of freedom. And the degrees of freedom is going to be your sample size minus 1. Now we have a couple things to calculate now. We need the standard error of the sampling distribution. Now I haven't used standard error yet when I'm discussing this whole review, but the standard error is just another way of saying what's the standard deviation of the sampling distribution. So I'm going to write standard error. I'm going to need a t-value. That will help us calculate the margin of error, which will help us get a lower and an upper bound for the intervals that we calculate. So we have a sample size of 36. We have a sample mean of 65.3, a standard deviation of 5.2. We're looking for a 90% confidence interval, so I just put 0.9. And then the degrees of freedom of this t statistic is 35. So the standard error is actually calculated the same way, except now we're going to use a sample standard deviation. We're going to do 5.2 divided by the square root of n, just like sigma over root n. So standard error is 0.866. Now the t-score. Just like with z-score, we need a value to multiply by our standard error. But with z, it was really just, is it 1.645, is it 1.96, or is it 2.576? And we chose each one of those numbers depending upon the confidence level that we were working with. T is always going to change depending on your sample size. So there really isn't any way to memorize what t statistic you're going to use. You just have to know the formula in Excel. So we're going to do t.inverse.2t. It's the easiest one to do. And it's going to be 1 minus the confidence level. So 1 minus 0.9, and then the degrees of freedom is 1 minus your sample size minus 1. And so I'm just clicking. I'm doing 1 minus our confidence level, comma, the degrees of freedom. And so in this particular case, our t-value is 1.6895. Once we get this, though, it's really the exact same. Our margin of error is just our standard error times t. And then we get our lower and upper estimates by doing x bar minus the margin of error and x bar plus the margin of error. And so we get a confidence level. They're all rounded to 1 decimal place, 63.8 to 66.8. Done. Now with the next couple questions, because I just did everything in Excel and I clicked the values, there really is no need for me to redo every single question. Now, if you want to redo all the formulas over and over again to get used to it, by all means, just look how I did it with question 78. But because I have input the formulas already in Excel, I'm just going to change the values, and it's automatically going to output the correct confidence interval. So with this question, we have 60.8, 66.8. I'm going to click that. Oh, it's question 79. So look how I did it with question 79. So question 80. Students in a stat class are conducting a survey to estimate the mean number of units students at their college are enrolled in. The students collect a random sample of 49 students. So my sample size is 49. The mean number is 12.2, that's x bar, and the standard deviation is 1.6. And we want a 95% confidence interval, so we're going to do 0.95 here. And then what will happen is it automatically calculates my degrees of freedom, which is n minus 1. It's automatically going to calculate the standard error, which is 1.6 divided by the square root of 49. And It's going to automatically update my t-score. And notice with t, normally our 95% confidence interval critical value is 1.96, but with t, it's 2.01. But in this case, because our sample size is 49, but what we get is 11.7 to 12.7. 81. So a doctor is measuring the mean systolic blood pressure of female students at a large college. Systolic blood pressure is known to have a skewed distribution. So the doctor collects systolic blood pressure measurements from a random sample. So the resulting 90% confidence interval is 100.4 to 159. Which of the following is true? Well, we have to look at the fact that it says that the distribution is skewed. And since it's skewed and our sample size is not 30 or more, the sampling distribution will not follow a normal distribution. So we can't make any conclusions. A researcher estimates the mean income of residents in a large city. The income variable is skewed to the right. So we select a random sample of 25. Well, the same situation here. No conclusion can be drawn. Each of the 110 students in a stat class select a different random sample of 35 quiz scores from a population of 5,000. Using their data, each student constructs a 90% confidence interval for the average quiz score. Which of the following is true? Well, because we're doing 90% confidence interval, what we're saying is out of the many, many confidence intervals that we calculate, about 90% of the intervals will contain the true value. All right, so we want to estimate chocolate chip cookies. They collect a random sample of cookies and count the chips and calculate a 95% confidence interval for the average number of chips per cookie and find that it's 18.6 to 21.3. So what does this tell us? Well, we're 95% certain that each cookie is brand. We expect 95% of the cookies to have between 18.6 and 21.3 chocolate chips. We would expect about 95% of all possible sample means from this population to be between, we are 95% certain that the confidence interval 18.6 to 18 or 21.3 includes a true average number of chocolate chips per cookie. Okay, so this just means we are 95% certain that the confidence interval of 18.6 to 21.3 includes the true average number of chocolate chips per cookie. In a statistics class, each student surveys a random sample of 20 students to estimate the number of units the students at their college are enrolled in. The college population is 10,000, so using their data, each student constructs a 95% confidence interval for mu. The average number of units to 10,000 students at their college are enrolled in. There are 40 students in the statistics class, so there are 40 different 95% confidence intervals. So, which of the following is correct? Well, about 95% of the 40 confidence intervals will contain mu, the average number of units that 10,000 students at their college are enrolled in. All right, 86. In a clinical trial of lung cancer, researchers measured reduction in tumor growth for a sample of 230 patients. The researchers used the reduction in tumor rate measurements to calculate a 95% confidence interval for the mean reduction in tumor rate to the new medication. So what does a 95% confidence interval for the mean reduction in tumor rate tell researchers about this study? If the researchers repeat the clinical trial many times, 95% of the time, the true mean reduction in tumor rate will be in the interval. Researchers are 95% confident the interval includes a sample mean. Nope. Researchers are confident that 95% of the 230 lung cancer patients will have a reduction. Nope. No. If researchers repeat this clinical trial many times, 95% of the time, the true mean reduction in tumor rate will be in the interval. So Justin and Haley conducted a mission to a new planet X. To study arm length. They sample 100 planet X residents, then they calculated a 95% confidence interval. So what does it tell you? Well, It just says, I am 95%, I'm confident that all of planet X residents will have an arm length within this interval. Is that wrong? No, gosh no, wait. Nope, I am confident that 90% of all planet X residents will have an arm length within this interval. I am 95% confident that this interval includes the population mean arm length. A high school statistics class wants to estimate the average number they collect a random sample. Yeah, okay. So, what is interpretation of the 95% confidence interval is valid? Didn't we just do this one? We are 95% certain that the confidence interval 18.6 to 21.3 includes the true average number of chocolate chips per cookie. Yeah, okay. Students in a statistics class conduct a survey to estimate, they sample 50 kids. So the students could produce a narrower confidence interval by increasing the sample size to 100. That is true. Increasing the sample size produces a narrower interval. Researchers took a random sample of 100 students and included 95% confidence interval. So the researcher could produce a narrower interval by increasing the confidence level to 99. That's false. Increasing the confidence level widens the interval. So we have a 90% confidence interval initially, and so true or false. The students could produce a narrower interval by increasing the confidence level to 95. So we're raising it, so false. Going from 90% to 95% will widen the interval. The researcher could produce a narrower confidence interval by increasing the sample size to 150. That is true. If we're going from 100 to 150, our margin of error will decrease. All right. Well, this is like the same question. The confidence interval based on a sample of 64 values will be more precise. That is true. 64 is a larger sample size than 25. Same question. The confidence interval based on the sample of 81 data values will be more precise because it has a larger sample size than 49. Yep, I think it's the same question. Okay. Oh wait, this one went away. The confidence interval based on the more precise. Why is that going? None of my other answers went away. Whatever. All right. Which confidence interval will have the greatest precision? Well, a confidence interval, I'm not even reading the questions because these answer choices all kind of just are self-explanatory. So which will have a greater precision? The one with a larger sample size. Why did this one keep going away? 90, 81, 81. That's weird. My answer for 94 keeps disappearing. None of my answer choices are saving now. All right, something's wrong with 94 and 95. They're the same question, so we're just going to ignore it, and I'll get one of them wrong. That's fine. 96. The confidence interval for a sample of 64 will be more precise. All right. 97. We constructed a 90% confidence interval, and then it says next, the students calculate a 95% confidence interval. Well, we have increased our confidence level, which means that the interval width will increase. 98. We constructed a 95% confidence interval, and suppose that we now compute a 90%. Well, we are decreasing the confidence interval, which means the width of the interval decreases. All right, now we're just constructing a bunch of confidence intervals. Students in a statistics class, let me go back up to 94. That's bothering me. Why did none of these save? 93. The confidence interval based on a sample of 64 will be more precise. All right. The confidence interval based on 81 will be more precise. 81. Yeah, it's like literally not going to let me do both. I think there's a mistake. Whatever. All right. 99. Students in a statistics class are conducting a sample to estimate the mean number of units their students are enrolled in. So I'm just going to do really, go back to the previous confidence intervals that we calculated. So we have a sample of 46 students. X bar in this case is 12.5. Standard deviation is 1.8. And we want a 95% confidence interval. So our degrees of freedom is automatically 45. We went and did, what? So if you recall, standard error is just the standard deviation divided by the square root of n. T, we just do t inverse dot 2t, and we do 1 minus the confidence level, comma, the degrees of freedom. Margin of error is just the standard error times the t value, and what we get is a confidence level interval of 11.97 to 13.03. Once again, once you have this all typed in, these confidence level intervals are really, really quick to calculate. So we have a sample of 43. We have the mean breaking weight of 774.3, a standard deviation of 15.4, and we want a 90% confidence interval, so 0.90. And then once we do that, everything is calculated for us. And once again, if you want to see how I did it, go back to the previous question that we looked at to see how I typed it into Excel. But we're using a t-score instead of a z-score because we're using the sample standard deviation. All right. This is like the same question. Okay. So we have a sample of 46 cables. The mean is 779, 15.4. We want a 99% confidence interval. Everything else is already formatted correctly, so it's 772.89 to 785.11. All right. 102. About 25% of college students report academic consequences of their drinking. A stat student is curious about drinking habits of students at his college, so he wants to estimate the mean number of alcoholic drinks consumed each week. So he wants a 95% confidence interval, so he takes a random sample of 51 kids, finds that the sample is 3.85 per week, and the standard deviation is 3.56. And we want a 95% confidence interval, so 0.95. And so we get from all this, having it already typed in for us, is 2.85 to 4.85. And you could even try doing it just with me, like try doing it yourself and see if you get the same numbers. All right, literally, the next two questions are the exact same. So all we're doing is changing the confidence level and other stuff. So we have 65 students. In that sample, about 3.91 per week. Standard deviation is 3.49. We want a 90% confidence interval. So we get in this one, it's 3.19 to 4.63. Same question. We surveyed 57 students. X bar is 3.89. Standard deviation is 3.52, but we want a 99% confidence level. Once we change those four values, everything else is given to us. So 2.65 to 5.13. All right. Now, these last two questions on the review are slightly different because now, if you read, I'll read it, we're going to be given the population standard deviation. So all the other confidence intervals for means that we calculated, we use the sample standard deviation. Not anymore. If we're given the population standard deviation, we don't need to use t anymore. We can use z. So we're going to be given n, x bar, sigma, our confidence level. Actually, we don't even need that anymore. We get our standard error, our z, our margin of error, lower and upper. That's all we need. So here we have the SAT. So we know, assume that individual SAT scores consistently have a normal distribution with standard deviation of 100. So that's our population standard deviation, sigma. An educational researcher wants to estimate the mean SAT math score. So the researcher chooses a random sample of 616 exams in his state. So N is 616. The sample mean is 501. So to calculate the standard error, we do sigma divided by the square root of N. And with z-score, we want a 90% confidence interval, and we know because we're using the population standard deviation, we can use z for 90% confidence, that's 1.645. Our margin of error is then going to be the standard error times z. And then to get our lower estimate, we do x bar minus the margin of error, and we do x bar plus the margin of error. So rounded to 3 decimal places, we get that confidence interval is 494.372 to 507.628. All right, very last question. I'm not going to redo everything. I'm just going to type in what we have. So N, we want to, is smoking during pregnancy associated with premature birth? So to investigate this question, researchers selected a random sample of 125 women. The average pregnancy length for this sample of smokers is 263 days. From a large body of research, it is known that the length of human pregnancy has a standard deviation of 16 days. Okay? And we just want a 95% confidence interval. So we change our z-score to 1 point. Please click anyone on this page to sign in again. Uh-oh. Ooh, I'm going to be angry if it doesn't save. So let me really quickly sign back in. All right, well, whatever. We'll see what happens. So our z-score is now 1.960. So N is 125, X bar is 263, standard deviation 16, standard error is sigma over root N. All right, it looks to be right. So we're going to say 260.195 to 265.805. Let me see, though. I don't want to... Let's save this. Will it allow me to save? Let's see, let's go back to 93. That's bothering me. 64. I just want it to be right. Whatever. All right, let's submit. Let's see what happens. If it'll allow me to. Yes! All right, so review this attempt. Let's see what we got wrong. Oh, here we go. Oh, my answer disappeared, or did I not answer it? Oh, this is the same weird thing about the chocolate chip cookies. That question appeared so many times. So with number 84, it didn't answer the question. So how do we interpret the interval? We are 95% certain that the confidence interval 18.6 to 21.3 includes the true average. That question was on there before. So I think it's just like 94 and 95. But anyway, so all my other answers are correct. So I hope this video helped you, and good luck.